Dr. Barbara Helmkamp, and I didn't bring your bio with me, Barbara, I'm sorry. But she has her degree in physics, and she's worked in the oil and gas industry, right? And now teaches for Veritas Scholarly. Yeah, okay. And she's spoken before here, for our group, not here at Mount Zion, but for our Denver Society of Creation group, and she's one of our board of directors. So please welcome Dr. Helmkamp.
Do the tech first. So is that close enough to me, to my mouth to be heard? Okay. I don't have a pocket and it doesn't have a clip. So I have a pointer and a speaker and I have to forward. But anyway, it'll be fine. So here's a gentleman for you sweeping something under the rug. And he's sweeping under the rug a very tiny mystery. And that very tiny words for the people in the back that says very tiny mystery is due to a gentleman by the name of Dr. Dalrymple, who was the deputy director of the United States Geological Survey in the early 80s, when there was a trial in Arkansas, sometimes called the Creation Trial, where a gentleman by the name of Robert Gentry, who is foundational in understanding this interesting topic of mine today of the polonium radiohalo, was invited to speak at that trial as an expert witness for creation. So, but Dr. Dalrymple referred to the polonium halo as a very tiny mystery as a way of dismissing the significance of it, because there is no good explanation for it from the conventional science community. If we go back a ways, these are some older quotes, I know that. 1973, in Science, the journal, I quote, "Nothing in geology fully explains the apparent occurrence of polonium halos." And late 80s for the second one that's too low for the back to read from, let's see, what group was it? The Humanist Association that has a newsletter called Creation Evolution, or did at that time. And in that volume, I quote, "It was realized very early that their existence," meaning these polonium halos, "would cause apparently insuperable geological problems, since the relevant polonium half-life is of the order of minutes." So, you say, well, what's happened since then on this topic? And I will get to that. But I'm pretty much concluded that not a lot. That the conventional science community still has no viable explanation for the existence of the polonium halo. And so we need to get it out from under the rug where it has been swept. So the reason I have, guess what, up there in the corner, you might guess what that is, right? It's a very tiny thing that's caused a great deal of trouble. COVID-19. So the significance and impact of a thing is not based on its size. So then, my title, finally, The Mysteries of Earth's Age. And the title is actually not due to me. It's due to a gentleman by the name of Paul Phelps, who is the president of the Northeast Colorado Creation Group, who asked me to speak on this topic, but then changed his mind because it's a rather dense topic. So I hope you stay with me and can get something out of of it. But I'm speaking here and then next week with the Pikes Peak group on the topic. So get those polonium halos out from under the Persian rug, I guess is my point. So this is the book that Robert Gentry wrote, and it documents his experience with that Arkansas creation trial, as well as includes many of the papers he published in scientific journals, and has beautiful pictures in it that he took himself of many of these little tiny, though it doesn't look tiny on the cover, polonium halos. So that is a polonium-218 halo blown up many times over that he took a picture of himself. And let me read this quote again for folks in the back who can't see it. In his book he says, "I was faced with one of the most difficult decisions of my life, whether or not to testify as an expert witness in the 1981 Arkansas creation evolution trial." And in fact, it was a hard decision because he knew what would happen, and it's what happened. He lost his funding, he lost his job, he couldn't do his research. So he was right that it was a difficult decision, but should have our commendation for his courage. And the other book that I've drawn heavily from, that I was familiar with prior to more recently reading Robert Gentry's book, is the second volume of which is the results volume from the RATE project, radioisotopes and the age of the Earth, and a number of articles sequential to this that I have read, chiefly by the second editor who authored a good portion of this volume of results, Andrew Snelling. Oh, I forgot to read that quote before I covered it over. So I researched a little, as much as I could in the time I had, and not being at a university where I have access to every journal under the sun, what's out there that someone has tried to explain the polonium halo without the notion of accelerated nuclear decay, just as though it would happen conventionally. And there's a couple who are at two different universities, maybe they aren't anymore, but Collins and Collins. And read several of the articles written by, this one was by both of them, and many have been just by Lawrence Collins. And he says, "These creationists ignore the fact that uranium in the original magma would be continuously supplying polonium isotopes during the 5 million years of cooling." Well, I can very definitively tell you that it's not so. Andrew Snelling doesn't ignore anything. He is extremely careful and a very fine geologist who certainly did not ignore important facets of this topic in researching them. So, and I have more to say about Collins and Collins later. But let's get to what in the world is a halo, or sometimes called a radio halo for, not for like AM and FM, but because it's radioactive. So it's a tiny spherical scar, or sometimes refers to a set of concentric scars. And it's commonly found in granite. And I'm going to use granite in the broad sense instead of granite in the narrow sense, because there are all kinds of rocks that are like granite but are not exactly granite, and that's encompassed by granite. So these radiohalos, radioisotopic derived scars, are found in specks of mica, and specifically black, most commonly black mica or biotite within the granite. So there's a typical piece of granite, you like my blue pointer, with a penny for scale, and the little black specks are mica. And so there's a large sample of mica. You're familiar with mica, probably it peels off, and it has many applications in industry, and it's very beautiful. There's another penny for scale. So this is a very large piece of mica, but those specks inside the granite are small bits of mica. So these radiohaloes or halos are ubiquitous everywhere in granites. And granites, this big pink rock thing at the base of this feature with sedimentary rock on top is a Pluton. It's not from Pluto. Pluton is an upwelling of magma that never reaches the surface, so an underground volcano. And when it is composed of the ingredients of granite, when it cools, it makes granite. And so the granitic Pluton is describing this feature. Now, magma intrudes, forces its way through surface rocks, sedimentary rocks, rocks that are layers. And we understand layers of rock to have been laid down by much water and much erosion associated with a much flood, the global flood. And so here are just a couple of pictures of dikes, that's called a dike, where you see the magma had intruded up through very clearly sedimentary rock. And so the point of this being that this lava, or really magma, that becomes granite is younger in its placement or emplacement than the rocks that were laid down. So these would be considered not exactly post-flood, but that during that flood year when so much sedimentation occurred so rapidly that these magmas intruded into the sedimentary rock. And that's important because Robert Gentry sampled mostly basement rock to study halos. And so he felt as though it was associated more with creation than subsequent geologic activity, the rapid geology associated with Creation Week rather than the flood. But in the RATE project, part of what Dr. Snelling, and he had help I'm sure, did was to establish that these halos are found in rock that would necessarily be right coincident with or immediately after the flood. So it's not a creation thing, it's a flood thing to understand these objects. So back to our giant spherical star, just to give you a sense of size, these are about 10 times bigger than this annoying bug that makes us sick. That's of the bacterial variety. And I don't know any biology, so don't ask me anything about Desulfovibrio vulgaris. I just found him because of his size. And then it's about 1,000 times bigger than a virus. Okay, just to give you a sense of what in the world 20 microns is for a radius. Now wait patiently as the screen fills up. You see the sphere forming. So one of these halos represents from 100 million to 1 billion emissions. Emissions of what? Emissions of alpha radiation. So I have a little light bulb in the middle of our sphere to represent the source. And this source is emitting alpha particles, and it takes 100 million to 1 billion of them to form a single halo, a single spherical scar. So this is the geologic record shown in 3 columns, otherwise it's too tall. And so the bottom is the Precambrian, then go out to Paleozoic as it's named, Paleozoic, more Paleozoic, over here Mesozoic, finally Tertiary, and the very top somewhere up here is where the flood versus post-flood sediment boundary would be. So the majority of everything out there is flood sediment. And that's the opinion of many creation scientists now, and I agree with that. So these Precambrian granites very deep basement rock granites would have been what Robert Gentry focused on. But the rate work, sampling granites from across the geologic column, included Paleozoic granites and a lot more Paleozoic granites and Mesozoic granites and even some tertiary granites. So the other big boundary in this rock column is Precambrian versus Paleozoic, where it's called the Cambrian explosion of life, when the fossil record is suddenly filled with fully formed creatures of all phyla. And below it there is virtually none. And so it would be understood that the record, rather than of life, is a record of death, the death of all the creatures that died in that flood, preserved for us to study. The fossil record of the flood. Okay, so the reason I have those listed is just to give you a feeling for the magnitude of the study that was undertaken and published in that rate volume 2. So I have a fist there because each sample of rock that was gathered was about the size of a fist. And I have a 50 on a little lab slide there that you can't see in the back for the life of you, that it took 50 slides for every sample. And then on that slide were 25, or actually 20 to 30, it varied, samples distributed across that slide. And just altogether, there were about 100 samples, if you count them up, 31 in the Precambrian, 31 again in the Paleozoic, 39 in the Mesozoic, and another 8 in the Tertiary. If you multiply it all together, this adds up to 100,000 preps. And I'll explain the prep to you in a moment, because it's really cute. But anyway, what's the meaning of all this? Of the 31 samples, 19 different rock units represented, so about 2 samples per rock unit, from the Precambrian, in which they were found 1,788 polonium-210 halos, 23 polonium-214 halos, 2 polonium-218 halos, and 510 uranium halos. So that's a bunch. And then going over, but it's not as much as the Paleozoic, which swells in polonium-210 halos, 14,384 of them, and 1,331 of the 214, 390 of the 218, if I have my order correctly, and then 10,000 of uranium. Then it drops back down, but still very significant in the Mesozoic for the sample set he shared, which might not be big enough to be representative. You know, statistics are funny that way. But 1,463 polonium-210 and 175 uranium. And then once up to the Tertiary, they seem to disappear. Out of the 8 samples, only 1 sample showed any, and it's the one that showed up is kind of on the border between Mesozoic and Tertiary, so, or Cenozoic. So just to give you a feel for this project, so here I have for the Precambrian rocks where all these granite samples, fist-sized granite samples, were collected from road cuts everywhere. So it's kind of funny. Washington State, Idaho, a bunch in Wyoming, a bunch in Colorado. There's the Yemez granite that's quite famous from work done by Russ Humphreys in New Mexico, a bunch of stuff associated with the Grand Canyon. Then going over to Europe, we have the Helsinki granite and some other granite that was unnamed, and then a couple granites taken from Australia, which is where Andrew Snelling is from. So that's the Australian connection. And from the Paleozoic, Mesozoic granitic rocks, again, we're all over the western U.S., plus quite a few from the eastern U.S., North Carolina, South Carolina, Georgia, and then Norway instead of Finland, and some from England, the Shaft granite of England, and then a whole bunch from Australia, the western part of Australia, where Andrew Snelling had done a lot of work as a younger man, so he had a lot of data. And then for tertiary, again, we're all over the western part of the US. There's this one index band that's called up in the Cascades of Washington, that state that I'm going to come back to later, or shortly, I can't remember quite. And then this is definitely for later, that there are some of these halos found in coalified wood from the tertiary and also Triassic, Jurassic, all associated with the Colorado Plateau, so Four Corners region. As far as I know, there aren't any that have been found anywhere else, so it's kind of an oddity. So here's back to our big circular halo that's really not that big. So the radiation source, represented by my light bulb, identifies the type of halo. And there are really only 5. There's the uranium-238. 238 designates the mass number for that radioactive isotope, for those of you in chemistry. And then polonium, 3 of them for polonium, that are all daughters in the chain from the decay of uranium-238. And then there's a thorium-232 that is out there. Haven't gotten as much attention. They're not very numerous, but they're there. So what am I talking about with a light bulb? Well, you've heard of a photon. A photon is a particle of light. We have this particle-wave duality going on in our world where we describe things as particles and as waves at the same time, like light. And particles also like the alpha particle. So why is the photon or light called gamma radiation? It was the third to be discovered. First alpha radiation was discovered, then beta radiation was discovered, then gamma. And then later on it was figured out that alpha is helium nuclei, beta is electrons, and gamma is light. So it's just a form of radiation, if you think of it that way. So there are these little gems. I'm wearing a large one now in commemoration of all this great information. It's a zircon around my neck. My husband gave it to me. Thank you. But these zircon crystals are found in granites. And within them have a little tiny bit, or a little inclusion of uranium. And that's very common. This is just some of those zircons extracted from a deep well, the Yamez drill hole that, again, relates to work done by Dr. Humphreys. Anyway, so that's just to see what they look like. They come in all sizes, from gem size down to tiny grains, down to tiny inclusions, or really I'm calling the uranium the inclusion. But those little dots, those are just impurities. That's not the uranium. Those are just impurities in the zircon. Though they might be a halo. Anyway, the halos we're talking about then, so we're imagining this little crystal, and within it a uranium-238 inclusion in the middle of our sphere. And it's shooting off alpha particles, whatever it wants to according to its timetable, but they always go the same distance from the middle, and so you get the spherical scar. That looks like the same slide. No. Okay, so the uranium-238 halo, come on, purple, there you are, would take 100 million to 1 billion, to form, years to form. Where did we see those numbers before, the 100 million and the 1 billion? That was also the same as the number of decays. And I read that a few times over and scratched my head, and I did some calculations and understand why they're the same. It has to do with the size that the uranium inclusion can be in order to be able to see the rings. If it gets too big, it's no longer a point source, and you don't get a nice little set of concentric stars. But it's just a really amazing thing that for uranium, given its 4.5 billion year, it's very stable half-life, the number is the same, 100 million to 1 billion years, 100 million to 1 billion decays. That's 1 decay per year. For 1 billion years, to get one of these things, if you're going to hold to the conventional mindset. What stays still for a billion years that it goes undisturbed, that would still be present? Anyway, I'll come back to that. It's kind of crazy when you think about the numbers involved. So here's a graph for you that is weird. We have linear energy transfer on the y-axis and stopping distance on the x-axis. And this is for water, not for granite, because that's where it can be measured. And the stopping distance is in microns, or a millionth of a meter. And what it's showing you is that when you shoot, these are for alpha particles, when you shoot the alpha particle through water, it slows down kind of gradually and then abruptly comes to a stop, and then it's done. And when it comes to an abrupt stop, it creates heat. It's like friction almost, and it burns the scar that remains as the halo. And so that's kind of interesting. So the alpha particle, the helium nucleus, loses most of its energy at a characteristic stopping distance. And this depends somewhat on the medium. So you wouldn't necessarily expect the size of the halo in granite to be, or in biotite, to be the same as in the coalified wood, but they don't differ by very much, interestingly. And even the water, even for water, it's the scale of microns, so it doesn't even change that much. That's interesting. Why do I have guns? Well, the analogy to shooting off is used by Andrew Snelling in his works, where there's a hole in the middle, a bubble in the middle of the polonium halo that's like a smoking gun analogy. But if you're thinking of shooting these things, shooting all off from the center, I mean, I could put guns in a big circle and they're all shooting outward from the source in the middle that generates the scar. So imagine with me mica. Here's some samples of mica. It's a book of leaves that's kind of amazing. There's a penny for scale on one sample, large sample. So mica has just made it so that these things could be found, because you just peel off the leaves like a book and you see them, when otherwise it's not clear they would ever have been found. So just imagine cutting a plane through a sphere, and that's what effectively is being accomplished by the leaves of the mica. And I have a microscope here because these are viewed, it's all in microns. So that's the microscopic level, so it's just a regular microscope. It's not a scanning, tunneling, fancy atomic level microscope or anything.
At what power?
I'll show you, there's some pictures that show powers to see. So I'll point those out. And then why do I have tape? So Robert Gentry pioneered the method for studying these things with Scotch tape. Scotch tape would peel off a layer and then put a piece of tape on the back and then peel the first layer off and then put another piece on the back, and that way peel it down until you got layer after layer, and then they're mounted on the little slides, and then that's the 100,000 preps we're talking about. So it's very sophisticated, but it's the standard for how it's done. Scotch brand tape, no less, is what it says. So the flakes of mica naturally reveal a halo, like slicing an onion shows the concentric rings. It's almost like it was made to be discovered. But you realize that the reason why they had to take so many consecutive samples is because you only get the true radius of the scar in the stack of books for the biggest circle, the great circle, the equator. So that's what that's representing. So they had to very carefully go through leaves of mica to find and so they don't double count them also. So you only count one halo for one halo, and not for however many it would be in the stack. So this is painful. I know it's painful, but it's not painful for everybody. This is the uranium-238 decay series. And so now we're going to start the comparison, the uranium halo, the polonium halo. And understand where they come from. So there are 8 alpha particle emissions that occur when uranium-238 decays all the way to lead-206. There are a bunch of beta decays also, which are electrons as opposed to alpha. So the first alpha takes us to a thorium. This is kind of complicated, but never mind. The majority of it, you see there's a 99% goes this pathway. Just assume I've left that off. But our next alpha is once we have uranium-234 going to thorium-230. So there are 2 uraniums in this decay series. And then we get thorium to radium, radium to radon. So alpha, 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 alpha. We've used up 4 of our 8 alphas in this first line. And we get at the very end of this first line a gas. And that's very significant to the transport model that explains the existence of these halos from a young Earth perspective. The gaseous nature, it's a noble gas for you chemistry people, so that affects its solubility or saturation properties and so forth. It's rather short-lived. I'll go through that in a minute. But then we're hopping over, kind of like we did with the geologic column. Otherwise it would be too long. But we get to, so radon is repeated, just for the sake of seeing it with our eye. And then we have an alpha decay to our first polonium, polonium-218. Then another alpha decay to lead-214. Beta decay to bismuth, beta decay to polonium-214. Alpha decay to lead-210. Beta minus decay to bismuth-210. Beta decay to polonium-210. And finally another alpha decay to our end product, lead. So this polonium-210 radiohalo is the most common, but there are places where the other 2 compete with it. And there typically are more polonium halos than uranium halos in a ratio of about 6 to 1. That surprised me. I thought it was the other way around, that there were more uranium than polonium. So I still need to explain, half-lives. So as we go with each arrow, we have a time, and it's using scientific notation to explain huge numbers. But uranium-238 is very, very stable with a half-life of 4.5 billion years. That's pretty stable. So that half-life is just a way to describe a decay rate. It's the amount of time you'd have to wait for half your sample to have undergone this decay to thorium. So that one's 4.5 billion. Then just 24 and a 10th day for thorium-234 to beta decay to, to PA. I'm having a blank on PA, and I'm a chemistry teacher. Help me, Candy. What's PA? She's looking at it.
I have a periodic table on my phone.
Do you remember? Pascalium or something? No.
We'll get it.
Okay, we'll get it in a minute. I made up Pascalium. Okay. My chemistry students would find this very amusing.
I know.
Okay, so then we're just going to jump over PA, Pascalium, to uranium-234. And here we have now 2.5 times 10 to the 5, that's 100,000 years. So another long decay. And I don't know why that's floating up there. It needs to be deleted. Okay.
PA is protactinium.
Protactinium. Okay, there we go. Then we get, the next one is on the order of, 7.5 10 to the 4. That's 75,000 years. And then 1,600 years for radium to radon. Then radon is just 4 days or so. Polonium-218, 3 minutes. And then our next alpha, polonium-214, 164.3 microseconds. Micro is a millionth of a second. Very, very quick. And then our last polonium, or alpha decay, is 140 days. So the long ones are in the top row. Whatever that means. Okay, so uranium halos cannot form in mica without a zircon grain locking the uranium's decay products inside it. Zircon's very hard. polonium halos cannot form without accelerated decay of a nearby uranium source, generating plenteous radon gas. So this is what I need to convince you of, what I convinced myself of. But again, the uranium halo, which contains all of those alpha rings in one onion-like thing, does so because the majority of its daughter products stay inside the zircon, like my gem, grain that's holding it in. The only one that leaks out is the gas, because gases are leaky, especially noble gases. So the radon leaks out, it diffuses out, but the others stay in there. So that's why radon, the gas, it's the escape mechanism to seed the polonium halos nearby, according to the creation model, which is the only model, in my opinion. Okay, so here is a uranium halo. It doesn't quite look like it has 8 rings, because some of them are very close to each other and they blur together. But this is the characteristic signature of a uranium halo with all those rings going out. And they have been labeled, you can see them labeled here, one going from in to out. We have, or is it out to in? Let me see. In to out. We have 1, 2, 8, well, one counting, one outward. 1, 2, 8, and 6, for whatever reason, are labeled on the left, 3, 4, 5, and 7 on the right. And if you look really careful, some of them are very nearly coincident. So it looks more like it has 5 rings, or 5 they're really concentric spheres, but we think of them as rings because we peeled it off with mica and it looks like a ring. So there is that hint. You might not have seen it. I'll back up so you can. It's bare. You have to, from way back there, you probably don't see it. Closer up, people see that little vague ring way out there. That's the very short-lived polonium-214, which is the biggest ring. And so you can measure these, and over again, they're the same size. It's about 35 microns out to that outer ring. And one of the earlier geologists who worked on this by the name of Henderson and Turnbull, I had fun digging out his data from Royal Society of London proceedings, and these are his numbers for the radii, just for the fun of it. And you have a radius associated with each one. You can see 3 are grouped together at 15.4, 2 together at 19.4. These are all microns. Polonium-214 is the largest at about 35, and also the shortest half-life. And there is a correlation there. The short half-life, it's very weak, but the shortest half-life is the biggest ring. And the ring size is related to the energy of the alpha particle that's emitted. So here's some pictures of polonium halos as opposed to polonium-210. That one's a polonium-218. The polonium-210 is just the one ring. One ring with a bubble in the middle. The bubble in the middle because there's nothing there anymore. It used up all of its everything to go to lead, and the lead must have dissolved. So, but the key point of that bubble is that there is no uranium there. Because that was the argument in the early days, that these are really just uranium halos and you just don't know what you're looking at. Well, it's been carefully studied by many, and that's not the case. The uranium halos still have a lot of the uranium in them because it hasn't decayed away. But these have nothing left. It's a transport phenomenon that carried their source to them temporarily, and it lost in short order, 140 days half-life. So, and there's your magnification, 500 times for this at the book level. That's a plate in a book. So it was 500 times magnification. So the argument is that how do we get that source in what would cause material radon escaping a zircon to collect in a particular location nearby and make another halo that requires 100 million of those radon particles. What would cause that? Well, radon doesn't have any affinity for anything particular, so the idea is that it has to first become polonium, which doesn't take very long, 3 days for the half-life, and those poloniums in their 3 minutes of lifetime are attracted to sulfur impurities or maybe chlorine impurities, sulfides and chlorides, and precipitate because they're not soluble, and then that becomes a site where they all want to go. It becomes the party. It aggregates, that happens with precipitation, and so you gradually build up a little speck, but it's disappearing as quickly as it builds up in 3 minutes, and generates its 100,000 decays to make that one spherical shell we see. And then it's 100 million. See, I say that wrong. 100 million, or even a billion. So that's thought to be the mechanism, but it has to happen fast, very fast. So I'm just showing in this table where the polonium-210 lies and which radius it has, about 20. You can see it's smaller than the big 218 that includes that 214, because it's between 218 and 210, so it includes the big ring. And you can see it has 3 rings, but whereas the polonium-210s only have 1. It's so cute. It is so cute. Okay, the next one we'll look at is the polonium-218 halo, which has the 3 rings. And here are a couple examples of them. One from the rate work, one from Gentry. And it has 3 rings because there are now 3 poloniums. So once the polonium gets caught there, apparently its products get caught there too. And so I guess when polonium sulfide becomes lead sulfide, then it still just stays put. And as the precipitate, and then it becomes, I don't know if there is such a thing as bismuth sulfide, but there is another then polonium sulfide, and then another lead sulfide, and then there's that bismuth again, so there must be a bismuth sulfide, and then finally the polonium-210. So it has 3. You never have, for 218 always has 3, 214 always has 2, 210 always has 1, uranium always has 8 that looks like 5.
So what is moving?
I'm getting there. Okay. I'm just slow. so this was my point, that there's, especially now for this 214 halo, that half of it disappears in 164.3 millionths of a second. It's just gone in instantly, practically. So it doesn't seem like it's possible that it could float around and then precipitate and build up to form our site, our source. So that's where I think it's quite likely that it's the lead, that maybe some lead gets away from that site, and, or excuse me, some of the lead never went to us. Some of the lead, let me say this again, some of the polonium-218 that became lead-214 never got to a source. It's just floating around in the water, and then it makes its bismuth, and the lead-214 is what then joins up and becomes the source of a polonium-214 halo. It's the only way to explain it, given its short half-life, to go back to a precursor. But those precursors might be involved also in the polonium-210, because it's got a lead and a bismuth to be a precursor also. So what is this dense data set? Well, I'll tell you. This is the table with all these rock samples and their halo counts, table 2, from the rate volume 2 that Snelling put together. And so you can just count them all up. That's the polonium-210 counts, polonium-214, 218, U-238 are the only ones I did. This is the Paleozoic granitic rocks. You add them all together, you get that 14,384 polonium-210. and the 1331 polonium-214, 1,300 polonium-214s. Those are those ones that have this 164.3 microsecond half-life. It's crazy that they would be there, but there they are. And that is the existence of the 214 halo is what caused Robert Gentry to argue that these were created, that they were in situ created, part of creation, because he could see no way for them to exist. Especially with his only having looked at, or primarily looked at the basement rocks. So he saw this as a creation statement. But then, as I explained to you before, they're all over in these Plutons that are, would have to be dated or associated with sedimentation from the flood, and so that doesn't hold up. So that's why I have it red, just because it's so remarkable. And I'm not going to bore you too long with these numbers, but this is the Mesozoic bunch with the one tertiary sample that thrown in at the top, that index granite from the Cascades. And I just point out that its supposed age is 33 million years. MA means million years, mega anna. But it takes 100 million years to form. So if you have inconsistency within the conventional community for the existence of that those two uranium-238 halos in this 33 mega anna index granite. Index granite means they're sure of their dating, or at least of, and as creationists we're not holding to those dates, but the sequence of them is useful and in understanding the events of the year of the flood itself. So understand that I am not claiming anything is that old. All right. I think I went to, yeah, okay. So this is now, let's get at the transport model. So here side by side, this is due to Snelling, his missing bullets discussions published, it's Enters in Genesis or ICR, I can't remember.
ICR, probably.
Is it? Okay. But here you have the uranium-238 radiohalo surrounding a little zircon, radioactive zircon crystal source, radioactive because it has uranium inside it, and adjacent to it, a polonium halo. And those lines are the leaves of the mica, which are like natural cracks for water to flow. Because things are happening too fast to count on just diffusion. You need motion. And often it was found that these centers lay in exactly the same mica sheet. So this is, to me, about the strongest argument there is that this one is the source for that one. Somehow, it just begs it, okay? So the lead-206 dissolves away, leaving a bubble in the middle of the polonium, whereas there's plenty of uranium left inside these when they're analyzed. So they're not empty, but these are empty.
The smoking gun.
So what just came up that added to it? I don't see anything. Okay. So the point being that these often are but a few millimeters apart. Their centers are often found on the same cleavage. And it's just begging that you would think of these as daughter and parent halos. The apple doesn't fall far from the tree. I was going to bring I thought about bringing a big bag of apples and passing them out so you'd remember. This is just getting at the idea that your lines will blur together. So this is just some work I did to figure out that the micron size source that I was finding in the literature made sense with the minimum number of decays and all that. I'm just showing you I did my homework. So, at a more recent paper I read, due to Snelling, he referred to a granodiorite, which is a little different composition than a granite, in which it was mostly polonium halos that were found without uranium halos. But that doesn't mean the zircon crystal sources weren't there, just that they were either too big to make a halo, and that's characteristic of the granodiorite, or they didn't, and where they weren't forming inside of mica. You have to have the mica that you can peel off to find them. So the absence of being, either not being in the mica or being just too big, you don't get a uranium halo, but they still have the radon that leaks out and then sources the polonium that finds its way to a site, a new source site. So this is just showing that sometimes these radiohalos occur not on a crack and sometimes on a crack. And what this supports that, so the cleaves of the mica are natural cracks, but you can have other kinds of cracks, and when you have them, it's very clear that these tend to form on them, which is arguing for water transport. And that's Dr. Snelling's model. And this shows the model. If you start with water is the chief ingredient. If you don't have a lot of water, you're not going to get the halos, even if you have the radioactive materials. Water is produced as granite crystallizes, and that's a big deal. That's what transports the radon gas that leaks out of the zircons. As the granite is crystallizing, it forces water out, and forces at this really high speed of 5 centimeters a day. But that's what you can get. But you're pushing water through the leaves of mica. It's not going to go very fast. But when the water is too hot, you don't get any halos either, because they get annealed away. My beautiful zircon gem has no impurities because it got cooked before I bought it, which annealed any impurities away. So you can't get the halos if the temperatures are high. And you have to drop below the annealing temperature, which has been determined to be 150 degrees Celsius. So as long as you're up high, higher than 150, you can have alpha particles going off, producing, radons that leak out, and then you get poloniums, and who would care? It's just going through the water, the direction of the water is left to right. But when the temperature, so the little red thermometer is showing it's higher than 150, so it's still too high, nothing's happening, but there's our little sulfur defect, just waiting to attract source material for halos. But we don't get any fission tracks or halos. Fission tracks are just single lines, burn trails for a single alpha particle. This is what particle physicists look at all the time when they do crash things into one another at accelerators. So then temperature is dropping, so we're having our polonium sulfide precipitate. There's some radon still floating around. There are uraniums over here. Temperature now dropped below 150, and so now our alpha particles generate halos, and both of them form. The uranium halo could not have started forming until the granite cooled. So that argues also against, remember, it takes 100 million to 1 billion years to form one. But this magma that is welling up as a Pluton has to have cooled. Now it was thought that it took forever for granites to cool, but the conventional community has decided it doesn't. And I'm running out of time. Oh, terrible. So I have just a couple more slides and I'll just have to cut it short. But this slide, again, due to Snelling, is showing you that the right conditions for both halos to form, particularly the polonium halo, last about 6 to 10 days. That's the only window you have, because the speed of the water expelled by the crystallization of the granite decreases as the water cools. But you can't form the halo until the water cools enough. And if you follow through, so the temperature is on the x-axis, y-axis, time in days on the x-axis, and we have the granite magma with zircon grains already releasing radon. Polonium intrudes into surface rocks. The first mineral grains begin crystallizing. The biotite crystallizes around the zircons. All the mineral grains are crystallized and stable. hot fluids are released, expelled by the granite, and that's the transport mechanism. But the time you have is based on the half-lives. That's where this scale comes from. And then you get to a point where your temperature is low enough not to destroy the halos, but not long later it's too slow to transport the radon. So it's a very, very short window, a time temperature window. And interestingly, since the days of Gentry, it has been put out there by conventional scientists that granite forms catastrophically. And so it doesn't take the million years to cool it was always thought to have done or form. That it's more like lava in its rates of both swelling upward. It's not a slow process of swelling upward. It's a very fast shooting up and then rapid cooling. And the cooling is highly dependent on how much water there is. And tell me what there was a lot of at the flood. You know, there was lots of water, so the magma itself had lots of water in it. And in fact, I've heard it said that one of the main things that comes out of a volcano is steam. So lots of water associated with it. So lots to read here, but granite formation, rapid dynamic process with very rapid ascent of granitic magmas in narrow conduits. This is conventional science. Not conventional, but not creationist. In between, I guess. People who recognize that the story that had been the story was wrong. And it's a total misconception also that large crystals found in granites required slow cooling. That was another song. That in the lab you can get nice big crystals in as short a time as an hour. And there's very little doubt among geologists now that granite is magmatic, that it cools directly from magma. Because of work that was done, that you can create granite in the lab, and it has mirrors properties of the granite in situ that is rather convincing.
Oh.
So
that's a significant development.
So the point, yeah it is, so the point that I'll probably have to try to end with soon is the signature of accelerated nuclear decay is the apple not falling far from the tree, the time temperature window that demands that, and I haven't even made this point properly, that the uranium shoot off its bullets a lot faster, way faster. And why, oh gosh. This is a bunch of work I did myself to convince myself of this. But there is no way at today's rates you can get polonium halos to form. And I don't have the time to go through this, but I would another time perhaps. What I actually did was look at groundwater samples and maximum amounts of radon activity found in groundwater, and used that to norm the solution content that if you're going to argue that these radiohaloes formed without a direct source nearby at an accelerated rate, you're stuck with these very low concentrations that are connected to the very slow decay rate of uranium. And so when you do that, and I can't explain it, so I'm not going to right now, but it's quite clear you need an adjacent, maybe it's just clear to you already, but that you need your source, the parent halo, or the parent zircon, spitting out way faster than one particle every year in order to get a halo to form in 6 to 10 days. Yeah, exactly. Right, thank you. So this is just these very funny halos that formed in this coalified wood that are double halos. These are the uranium-210, not uranium, polonium-210 halos that got squashed. The sediment itself got compacted and squashed it into an ellipse, putting a time constraint on, oh, I'm just showing you ellipses, putting a time constraint on the ellipse that wasn't an ellipse to start, forming in a couple years, and then the second one in less than 4 years to have this record. This coal, or this wood, had to compact and begin to form coal in 4 years. So that's an indication of the rapid rates of things happening during the flood. But I also think it's impossible, aren't any uranium ones in the wood, but I think it's impossible to not have accelerated decay even to get these, because the concentrations of groundwater just don't do it. They don't do it. And when you're at the high temperatures you have to be at to get halos to form, then uranium, because the radon comes from the uranium in solution is very low. It's got to be coming from the nearby solid sources, but they've got to be clocking a lot faster, or else it's just not going to happen. So it's the signature for accelerated decay. It's some more of my modeling and groundwater data, and I'm just going to jump forward to here and end. This is one of my possible ending points. So what in the world does this have to do with anything? So there's a miracle that is taking place here, because we don't understand how accelerated decay would have happened. There's some modeling that's been done to suggest changes in the strength of the nuclear potential can have impact on half-lives of the order of 1,000,000-fold. That's done by Eugene Chapin. It was also part of the rate work. But that's still just displacing the miracle. Okay, so who then changed the strength of the nuclear potential? So you're displacing the miracle. And there's some other issues. There's a lot of heat that would be produced. Where did that heat go? Because you accelerate that. And all those little burn marks are friction that's generating heat. And yet the heat that it produced didn't prevent the halo from forming. So something was happening to that heat. So we've got some miracles. And here's just a beautiful manuscript picture of the empty tomb. We have a miracle there too, right? Finally you come up against the miracle. You can confine it. You can say, well, the tomb, Christ died on one day, and then the tomb wasn't empty, and then it was empty, and so you know that the miracle happened between, those two time frames, and you know where. Maybe we don't know exactly. I think we do, but you can confine the miracle. But in the end, it's a miracle. No one is going to explain rising from the dead. It's a miracle, and so I think we're bumping up against that with the events, both of creation and the flood. Not that there are many things we can't put limits on and understand, and it's great fun, but anyway. And then this other tombstone, so here's the tomb that's empty, here's the tomb that's not, and this one is from the early 1900s. It's a Jewess buried in, I think it was Corinth. I have to look at my notes again, but that doesn't matter so much. Look at the date. It's dated from creation. So this relates to the Judy's, or our Denver Society of Creation's overture written by Pastor Flammy regarding the age of the earth, and those genealogies. What would you do with numbers except add them up? Well, what did the Jews do with the numbers but add them up? So just a reminder, just a way to pull that in, actually. So I'm going to end there with not having said half of what I wanted to say, but having used every bit of an hour. And I will take questions.
We probably have time for just a couple of questions because we're running over here. So, but if anybody has a burning question.
Burning question about the halos.
So if you do decide, if you come up with a question here in the next few minutes, Barb will be around
Yep,
afterwards. Okay. Thank you so much. I
Sure.
appreciate it.
Yeah.